Okay, so Zackory is a PhD, so Zackory Erickson is a PhD candidate at the Georgia Institute of Technology, and he is advised by Professor Charlie Kemp. And he received his master's degree from Georgia Tech and his bachelor's degree at the University of Wisconsin, La Crosse. And starting from this fall, he will join Carnegie Mellon University as an assistant professor, so congrats. And his work has won the Best Student Paper Award at ICRA 2019 and a Best Paper in Service Robotics finalist at ICRA 2019. And his work spans the fields of physically assistive robotics, haptic perception learning, physics simulation, and human-robot interaction. So the floor is yours, Zackory.
Thank you. Let's try to share the screen here. Oh, second. Let's see. If I share this.
Yeah, perfect.
Then, oh, I can't. Play. There we go. All right. So do you see this?
Yes, perfect.
Awesome. So, hello everyone. I'm Zackory Erickson. Thank you, Martina, for the introduction. You covered pretty much my entire beginning slide here. So I'm going to share with you some of my past and ongoing research on leveraging soft body physics simulation for developing intelligent robotic caregivers. But first, before I begin, just a little bit about myself. This is kind of things Martina's already talked about at this point. I'm a fifth-year PhD candidate in the Healthcare Robotics Lab at Georgia Tech, where I'm advised by Charlie Kemp. And in the fall, I'll be joining CMU as an assistant professor in the Robotics Institute, and I'll be building a lab focused on robotic caregiving. So my research focuses on intelligent physical assistance. Robots are in close physical contact with people. These robots aren't just standing next to a person, they're touching the person, applying force, sensing, and manipulating the human body. An example from my research on what this close physical interaction can look like is bathing assistance, where a robot is using a wet washcloth in order to clean off a person's body, or dressing assistance, where a robot is helping someone with disabilities put on a fresh set of clothes for the day. Robots present an opportunity to have a profound impact and improve the quality of life for millions of older adults and people with disabilities. And what I'd like to focus on in this talk is robot-assisted dressing, the task of manipulating cloth around the human body in order to help someone with physical disabilities get dressed. Now, since safety and comfort are important during this process, one natural question for us to ask is, can a robot estimate the forces it applies onto a person? Yet for the task of robot-assisted dressing, this question can be a bit difficult to answer. First, deformable cloth is making contact with a person, which results in these complex force distributions. Visually estimating the coupled cloth and body state remain exceptionally hard today. And it's difficult for robots to take on a person's perspective. Our summator sensory system, our skin, it's wonderful for us, but it's not particularly useful for robots. It doesn't provide robots with much data. So to overcome these challenges, we've designed a physics-based simulation environment, which allows us to simulate how fabric applies force onto the human body. This environment consists of a few different elements. First, a robotic end effector, pulling on the sleeve of a hospital gown onto a simulated arm. And the colors that we see on this arm are what we call a force map, where each color indicates different levels of force being applied. Blue is low force, red is high force, being applied at specific regions along the arm. And what I'd like to show you is how robots can use low-dimensional haptic measurements from their end effector in order to estimate a high-dimensional force map across a person's body in real time during assistance. This will allow a robot to take on a person's perspective and view this task from a person's point of view in terms of how the person is having forces applied onto their body. So again, I'd like to share with you a novel technique in which robots can use low-dimensional local measurements from their end effector, think sense of touch here, combined with learning using temporal features in order to estimate high-dimensional forces applied onto a person's body by deformable fabric. Now, these force maps look continuous and smooth over the arm, but they have a discrete representation underneath. So let's briefly look at that, since it's going to impact how we learn these force maps. So the human arm is discretized into 300 force sensing points. You can think of these as little force sensors all over the arm. A vertex on the deformable cloth mesh will make contact with the simulated body at some arbitrary position X, and it'll apply some force F. And what we're going to do is distribute the magnitude of that force to the nearby force sensing points on the limb. And if we were to just color each of these force sensing points according to how much force is being applied to each one, we'd end up getting a figure that looks something like this. And then what we do is we perform an interpolation over all these points in order to generate a nice smooth force map along the arm. And so now what we'd like is for robots to be able to estimate these force maps. And the way we do this is by building an estimator, a function f, that takes as input prior measurements from a robot's end effector, as well as a current measurement from the robot, and then uses this to estimate a force map across a person's body. And it's important to note here that this estimator does not have an explicit model or observation of the fabric, right? It's estimating these force maps just from end effector measurements alone. So now we're going to be getting these measurements in simulation from the end effector. This includes haptic and kinematic measurements, force, torque, and velocity. And in terms of the real world, these measurements are also going to be quite easy for us to collect. We're going to be doing so using a force torque sensor, and this sensor will be connected to the fabric garment, which the robot is also holding. Now, in terms of implementing this estimator, we're going to do so using a recurrent neural network. And at every time step, this network is going to take as input these 9-dimensional end effector measurements, and then output an estimated 300-dimensional force map across a person's limb. And here we're using a long short-term memory or LSTM network for this estimator, but there are certainly other types of architectures or temporal networks that would work here. What is important is to have some form of model that leverages temporal features in order to make this mapping tractable from a 9-dimensional input to a 300-dimensional output. So we can now train this recurrent network using simulation. We perform 5,000 randomized dressing sequences in physics simulation, where the robot is just moving around randomly in a self-supervised fashion with the goal of collecting lots of data of how fabric interacts with the human body and applies force onto a person. And so now we can collect lots of data from simulation and train our estimator on that. But what happens is that if we just try to naively use this estimator, we end up getting some really weird scenarios like this, where the trained model is estimating these tiny forces all over a person's body. And this is just regression error. This is error in our recurrent neural network, where the model is constantly estimating these small forces all the time, even though the cloth isn't in contact here. So to overcome this, we build a contact map, which a robot will also be estimating. And just like the force map, this contact map will have 300 points, one for each corresponding force sensing point on the limb. And this contact map is set up just like a binary classification problem, where for each point along the arm, it's going to be assigned a value of 1 if the cloth is applying some non-zero force at that point. Otherwise, the contact map will receive a value of -1. And then if we bring this back into our recurrent neural network, we're now going to be estimating both the force map across a person's body, but now also this contact map, so a 600-dimensional vector that we'll be estimating. And what we can do after performing an estimate is loop through all of the forces in the force map and zero out any of them in which the contact map indicates that there's no force being applied. Right, so this is going to allow a robot to estimate both how much force is being applied onto a person, but also if force is being applied at specific regions along a person's body. And again, this is just to overcome these small errors in our regression model. And in practice, we find that it works quite well. So let's look at that. How well are we able to estimate these force maps in simulation? On the right-hand side, we're showing the ground truth force maps from simulation. This is the forces the fabric is actually applying onto the simulated arm. And on the left, we'll be visualizing the estimated force maps, which is the output of our recurrent model. And so here we're looking at two different scenarios of this hospital gown being pulled onto the arm. In the first case, the sleeve of the hospital gown is being pulled onto the forearm. It's going to kind of tug and pull at the elbow there. And in the second case, the sleeve is going to miss the forearm entirely and just get dragged over the upper arm. But what we're seeing is that in both instances, the estimated force maps from our model are closely aligning with what we'd expect to observe from simulation. And this learning-based technique also generalizes to other tasks with deformable fabric, such as pulling a pair of shorts onto a leg, where here the shorts get caught on the heel of the foot and start to tug and apply force there. But the big question is, can this generalize to real robots interacting with real people? It seems possible, since our recurrent network only needs measurements from a robot's end effector. It doesn't need to know anything about the state of this high-dimensional cloth. But instead of just estimating force maps, let's take this one step further and look at how real robots can predict these force maps into the future. Doing so will allow us to explore the question, how will a robot's future actions apply force onto a person? Can we select actions that minimize future force? So in order to predict force maps into the future, we're now going to set up two different models. The first, both a predictor and an estimator. In this first model, the predictor is a function g, which is going to take as input prior measurements from a robot's end effector, along with now a set of proposed future actions for the robot to execute. And then given this information, we want our predictor to output a set of predicted future measurements that a robot could expect to observe if it were to execute those candidate actions. And here H sub P is the prediction horizon. That's how far into the future the robot is looking. And if you're familiar with what a dynamics model is, this predictor is essentially a dynamics model. And in order to map measurements to force maps, we're going to use the exact same estimator that we've already trained, that we saw just a few slides ago, but I want to change the notation of it a bit here. So this estimator is again going to take as input prior measurements, but now also take in these predicted future measurements. So we're going to pass the output of our predictor into our estimator. And then we're going to use this information in order to output a predicted force map and contact map across a person's body. And again, we're using the exact same estimator that we've already trained, that we saw just a few slides ago. But what's really cool about this approach is we can now start to do function composition, where we have f of g, and that's going to allow us to go directly from robot measurements and future actions straight to a predicted force map across a person's body. And so now if we piece together our predictor with the estimator, we can predict force maps across a person's body that a robot could expect to observe if it were to execute those candidate actions from the left-hand side. And in terms of implementing this predictor and estimator, well, the estimator is really easy. We've already implemented it and trained it, so we're just going to use it here. But now for the predictor, we're going to use the exact same recurrent neural network architecture that we used for the estimator, but we're going to train a separate model. This model will have different inputs and outputs. And a nice thing about this is that we can use the same self-supervised training approach from the estimator that we used to train the estimator to also train the predictor. So we'll collect thousands of randomized dress-in sequences in simulation and use all of that observed data to train the predictor. So we now have a model to predict these future force maps applied onto a person's body. How do we use these force maps to control a robot? Well, we do so using a technique called model predictive control, in which we select actions that minimize the cost function shown above here. And now I apologize for throwing just a bunch of arbitrary variables on the slides. Let's walk through what each of these terms are going to be doing one by one. This first term in our cost function is going to be minimizing the predicted forces across a person's arm. This is that term that's minimizing those predicted force maps that we've been looking at so far. The second term is going to be encouraging the robot end effector to move forward along the arm, essentially making and encouraging the robot to make task progress. And then the last term is discouraging the robot from rotating its end effector whenever possible. And so that's it to this controller. We then set up a human-robot study wherein a peer-to robot assists 10 able-bodied participants with the task of dressing on the sleeve of a hospital gown. And we're going to be looking at two different scenarios here. First, can the robot fully pull the sleeve of a hospital gown onto a person's arm? And then second, can the robot mitigate the cloth from getting caught on a person's body? And what we're going to be doing is varying the prediction horizon anywhere from 0.01 seconds all the way up to 0.2 seconds. And this is that H sub P, that prediction horizon that we're changing here. And so if we prevent the robot from looking very far into the future, what we observe is that the robot doesn't recognize that it's applying large forces onto a person's body until it's already too late and it's starting to tug and pull at the person's elbow here. Yet by allowing a robot to predict further into the future, the robot is able to recognize that it can continue to minimize forces by rotating around the elbow and pulling the garment all the way up to a person's shoulder. And the robot successfully pulled the garment up to a person's shoulder in almost all the trials that we had tested with participants. And similarly, by preventing the robot from looking very far into the future, the robot doesn't recognize that a garment is about to get caught on a person's hand and apply large forces until, well, it's already too late and the garment has gotten caught and starting to tug and pull. Yet by allowing a robot to again predict further into the future, the robot is able to recognize that a garment would soon get caught on a person's hand. It then lowers its end effector closer to a person's body, shown here by this red line. And this allows the robot to mitigate the garment from entirely getting caught on the person's body. So overall, we've seen a novel human perspective taking technique that combines low-dimensional end effector measurements with model-based learning for predicting high-dimensional force maps across a person's limb. And when we combine these predictions with model-based or model predictive control, a robot is able to provide physical dressing assistance while considering how the actions would apply force onto a person's body. So far we've seen how a real robot can leverage simulation in order to predict the forces applied onto a person's body and dress these deformable garments. And now at this point, I'd like to briefly share how we've been recently extending this concept of physics-based simulation for robotic caregiving, simulating many different robots and many different people with a variety of tasks, some of which include manipulation of deformables. And historically, there's been well over a decade of active work on designing robotic systems to physically assist people with tasks ranging from feeding and drinking to dressing to hygiene assistance, all of which require manipulation of deformable materials, whether that be food or clothing, washcloths, or just the soft human body. Yet in almost every case, it's a single robot helping a small group of people with only a single task. Robots aren't able to learn common sense about deformables or the human body that transcend multiple tasks or scenarios. And this is because there are some huge hurdles in the field of physical human-robot interaction. First, capable real-world robots are not cheap. Conducting human studies is also not that cheap, and this has arguably been one of the largest barriers of entry for researchers into the field. There are also risks associated with robots coming into close physical contact with people, and we would never want robots to accidentally hurt someone or put someone at risk. And lastly, collecting data and performing evaluations on a real robot interacting with real people is really slow. And this is especially true when working with people with disabilities. These challenges limit not only the kinds of research we can do, but who can do this kind of research. But what if we could use physics simulation to overcome these challenges? Recently, there's been a growing push for multitask simulation environments where we can train or evaluate robots across a large number of diverse tasks. Yet most of these are within a robot manipulation or navigation context. In fact, there's a complete lack of simulating robots physically interacting with people in any framework. So our research has recently introduced Assistive Gym, the first open source physics-based simulation framework for modeling physical human-robot interaction and robotic assistance. Assistive Gym is a framework for simulating both rigid and soft body dynamics towards developing robots that can physically interact with people across a large number of tasks, including those that rely on manipulation of deformable materials such as clothing or cloth. And what I'd like to share with you is how physics simulation can open up entirely new research directions and opportunities within physical human-robot interaction and deformable manipulation. We've introduced several physics-based environments for physical assistance, developed baselines and benchmarks for robotic caregiving, and we've investigated generalization of physical human-robot interaction from a number of angles, including human motion, preferences, and variation in human body shape and impairments. So one of the first research opportunities that we gain with simulation is the ability to train versatile assistive robots and develop control algorithms towards common sense reasoning. For example, we've developed physics-based environments where robots have learned to assist people with different tasks associated with activities of daily living, such as bathing, feeding, or dressing assistance. And these tasks are selected from literature such that if we have versatile robots that could help with them, it would have real-world impact and be meaningful to many people with disabilities. Physics simulation also enables us to establish benchmarks and baselines for physical human-robot interaction. And this is something that the field of computer vision has done remarkably well at, and I believe physical HRI can benefit from that same mindset. So towards this goal, we've introduced a set of baseline control policies with Assistive Gym, each trained with proximal policy optimization and actor-critic deep reinforcement learning technique. And we trained 24 policies, one for each task and robot combination in Assistive Gym, where each policy is trained for 50,000 rollouts, and we select the best policy out of 3 random seeds. And the first question we should be thinking about is, well, how well do these baselines perform in simulation? So when assisting a person who holds a static pose, these baseline controllers were able to achieve reasonable performance for several of the assistive tasks, including itch scratching, bed bathing, feeding, and drinking assistance. But it's also worth noting here that there's still significant room for improvement and future research. These are just baseline controllers. They're not solving the field of robotic care for us. And a very clear example of this is that all robots struggle to provide dressing and arm manipulation assistance to an inactive human. Yet by simulating physical interaction, we can now create reproducible benchmarks for assistive robotics. We can now quantify how various robots and controllers are performing when interacting with people across different tasks. And this table here shows the average reward the baseline controllers achieved for each task and robot combination, where bolding here represents the best robot for a given task. And creating physical interaction benchmarks like this is something that's exceptionally difficult and costly to do in the real world, especially when robots are having to deal with deformable materials. Another research direction that we gain with physics simulation is the ability to design techniques for generalizing assistive robots across varying human body shapes, weights, and impairments. So if you would like to train or evaluate an assistive robotic system on 50,000 people with different body sizes, disabilities, then simulations would take maybe 6 to 12 hours, fully automated. And on the left is a visualization from ongoing research where we're investigating assistive robots that can generalize across a large distribution of human body proportions, weights, and sizes. Yet in the real world, 50,000 participants is immediately disqualified. That is far too large of a number. And we instead think, let's just test on 10 able-bodied college students, and that'll still take a week to do a study like that. If we want 10 real participants with disabilities, it's a much slower process, and it could easily take over a month. Another really interesting research topic that becomes available is modeling human preferences and developing control algorithms that learn and adapt to a person's preferences. So Assistive Gym provides a reward-based structure for modeling human preferences, and what that allows us to do is train robots that adapt their assistance to different human preferences. For example, robots are penalized more for spilling water on a person rather than on the floor, and robots also learn not to apply large forces onto a person's body. But you also might be wondering if modeling human preferences actually matters. So what I'd like to introduce you to is one of the early development versions of Assistive Gym where we were not modeling human preferences. And here the robot has learned to help someone drink water using reinforcement learning. And as it turns out, the fastest way to get water into someone's mouth to help someone drink water is to really just catapult water at their face. So essentially just precision water throwing. And this is one of the reasons why I believe it's important to give robots common sense about deformable materials around people. Throwing water does solve the task at hand, but it's clearly not the right way to interact with people. So again, physics simulation opens up a number of exciting and new research directions for physical HRI and robotic caregiving, which our research has begun to investigate. There are also several other extensions or research directions that sadly, I don't have the time to talk about in depth today, but I would like to just briefly mention them. So we've investigated modeling and benchmarking human motion in Assistive Gym, where we used a co-optimization technique to learn collaborative human motion. And we found that pretty much across the board, robots are able to provide more successful assistance to an active collaborative human. Assistive Gym is also an evolving framework that's been adopted at other universities, and as a part of a collaboration with researchers at Stanford, Assistive Gym has been integrated with Gibson, which now allows us to simulate robots physically interacting with people in these visually realistic and interactive homes. And then additionally, there's a gap between simulation and real-world assistive robots. Yet there's also risks with just blindly evaluating simulation-trained robots with real people. So to overcome this, we've introduced Assistive VR Gym as a way to bring real people into physics simulation through a virtual reality interface to interact with and evaluate virtual assistive robots. So in closing, this is an ongoing and developing research direction. And what I've shared with you today is really just the beginning. We have ongoing projects and collaborations that are pushing cloth manipulation in Assistive Gym to be more robust when interacting with other objects, the environment, and the human body. Beyond that, I'm happy to talk about research offline and discuss potential collaborations related to ideas that I've shared here in this talk. And with that, I'd like to thank you for your attention. It's been a joy sharing this research with you, and I'd be happy to take any questions now. I also left a few minutes just so that we can have a discussion of physics simulation for deformables. So thank you.
Thanks a lot, Zackory. The talk was great, and we have a lot of questions. So first, at the very beginning of your talk, NA Yuan Huang asked how to evaluate your force estimation model.
Yeah, this is a great question. So how do we evaluate the force estimation and force prediction model? Well, I would say right now, actually, we're currently doing this. So I can provide a little bit of insight into how we're planning on doing this. So at least my initial response is that we don't currently have a way of evaluating whether the forces in simulation are matching ground truth force estimation, or the ground truth forces cloth is applying. Right? Simulation has been optimized to align these forces, but there hasn't been a closed loop process of evaluating is this correct. So we're currently doing this, and the way we're doing this is we have a deformable cloth simulator. It's a force sensor with about 200 or so deformable force sensors in it. And so we're putting this around the human body, around the human arm, and then pulling different garments onto it, and then validating whether the forces in simulation are matching what we're actually observing from the sensor on real people. It's a great question.
Okay, great, nice. Then we have another question from Yixuan Wang, and the question is, I'm curious how the estimator and the predictor will perform when training and test distribution is different. For example, training cloth and training arm can be different from test cloth and test arm. In addition, it seems that a human is assumed to be static here. What if a human actually moves during dressing?
Yeah, these are all very good points. So there's definitely a big question with what happens if the cloth in the real world doesn't match the cloth in simulation. That would absolutely, it's out of distribution in that case, and whether the models generalized to that is unclear, I would say at this point. The simulation that we saw there has actually been optimized based off of real world force data from pulling a hospital gown onto different objects and the human body. So the simulation itself has been optimized based off of real world data, but that's again specific to a certain type of cloth, right? So if you change the cloth, we would expect there to be different dynamics. And this is just a challenge with soft body simulation in general, is that there's lots of different types of soft bodies, including lots of different types of cloth. And at least currently, the ongoing approach to this is you need to collect some real world data and use that data to optimize the simulation. Right? So for each type of cloth that you'd like to use, there is kind of an optimization process to get the simulator to align with that. Now, in terms of, so that was a good point. In terms of the staticness of the human body, I also agree with you. The human body, at least in that work that I showed at the very beginning, was static. Some more recent work, again, doing the evaluations of that in the real world, there is some human motion in play there, but again, it's pretty minor. We're not seeing any significant human motion. And that's where, so that is actually definitely a limitation of that, that approach. And that's where hopefully we're looking at kind of breaking that in this future work with assistive gym, where we're actually modeling human motion. We've got controllers for humans at this point, and looking at how robots can, again, learn to do different types of deformable manipulation once the human is actually in motion, collaborating with a robot. These are good points. Thank you as well.
Okay, thanks. That was also the point that Julia from our panelists was asking. And then we have a question from Alberta Longini. So in the assisted dressing scenario, have you thought about how different properties of clothes, such as different degrees of elasticity of the fabrics, can influence the forces perceived by the human?
Absolutely. So we haven't actually done a full investigation of how much cloth parameters impact the forces. There is clearly, it will impact forces, right? If you have like spandex, something that stretches a lot, versus like leather, which has very little stretch, you would expect there to be a noticeable difference in the amount of force applied, particularly once the cloth becomes taut, which at the point at which it no longer stretches easily, right? So certain types of cloth will stretch much more easily than other types, and hence the forces applied will be significantly different. So we haven't, though, this is a good point for, I would say, future research, is actually investigating how those types of cloth materials actually impact forces. It's not something that has been done yet.
Okay, nice, thanks. And then we have Christian Kaufman. I'm sorry for the pronunciation. And so thank you very much, Zackory, for your talk. And he's asking, I was wondering if you also consider to implement and integrate sensor simulation models in your framework, such as proximity sensors, to further close the sim-to-real gap.
Oh, yes, I very much like this. So this actually has, I have some other research which is kind of touching on this. I didn't present it all in this talk. One approach to look at specifically a proximity sensor is capacitive sensing, in which it emits an electric field. So if you have capacitive sensors on the robot, those sensors will emit an electric field, and anything that conducts electricity will be able to be sensed by that. The human body is an aspect, is definitely an object or material that conducts electricity well. So by using capacitive sensors, you can use them as a type of proximity sensor around the human body. And so I have work on that direction. And I myself have not been simulating that, but one of my colleagues has been looking. Alex Clegg has been looking at simulating capacitive sensors in simulation as generic proximity sensors. However, that loop has also not been closed yet. So although we have begun investigating these types of proximity sensors in simulation, the loop hasn't been closed in terms of evaluating whether those proximity sensors do work with real robots, right? In terms of the difference, the gap between the simulated sensor and the real capacitive sensors. There is still a gap there, and we haven't fully closed that yet. So that's a really good point. So beyond that, there are a number of different types of sensors that can be simulated. Some are usually readily available in physics simulators, things like cameras, RGB, and depth cameras. Other types of cameras, though, are a little bit more unique, and I haven't seen many implementations of them, things like thermal cameras. And so I would say this is actually very much still an active research area in terms of how to simulate different types of sensors in simulation, especially physics simulation. A few of them, force and torque sensors, have been implemented, cameras have been implemented, but beyond that, there's and other things, torque kind of actuator sensors, encoders and such. Those have obviously been implemented in simulation, but there's a lot of other sensors that, especially haptic sensors, that are still very much open research field to look at in physics simulation.
Okay, nice, thanks. We have the last question, and it's Joanna Mizzoni. She says, thank you for the talk. It was a very well-rounded approach to physical human-robot interaction. And in the case of real-world executions of the assisting tasks, how do you think the active or passive compliance of the robot will affect the underlying estimation and optimization?
Oh, this is a good one. So I haven't actually put much thought into this. There is, and it might be slightly biased because of the robot that I'm working with. So I am working, at least historically, I've been working with a PR2 robot, which I have done some other work with a few other robots, including the Sawyer and Jaco, but predominantly the PR2. And there is a good amount of compliance to that. So I suspect some approaches some of this research has kind of that built-in notion that there is some compliance, right? The PR2 is a very, it does have compliance in its motors, its actuators are back drivable and such. So I would suspect that comes into play a little bit, especially, and I think realistically, when robots are interacting with people in a close physical nature or physical interaction, it is probably important to have robots that have this level of compliance, right? So they're a little bit kind of inherently safe from a mechanical perspective. So I suspect actually that kind of compliance is actually a very good thing. How it impacts the control, though, is definitely a big question, which I haven't fully investigated yet. And it would probably require looking at both robots that have less compliance compared to robots that have more compliance in the real world, right? So sadly, I would say this is an interesting research idea, but I haven't investigated this yet. But this is very interesting.
Okay, nice, Zackory. Thanks a lot for being here, and good luck with your workshop.
Awesome, thank you. I'll stick around here a little bit more just to see some other talks.
Okay, perfect. Okay, nice.